Hi. I'm here to talk about Clojure, which I've done several times and once at the European Common Lisp workshop for an audience of Lispers, but usually not. So it's always nice to talk to a crowd of people who already know Lisp, because then I can talk about more advanced things and more interesting things. I don't have to explain S expressions and things like that. But I want to make sure that that presumption is correct. Does everybody here know some dialect of Lisp? Yes? Anyone not? Okay. Somewhat. I'm not going to cater to you, so you're just going to have to hang on. And amongst the people who know Lisp, how many are of the Common Lisp persuasion? And Scheme? Okay. I won't make any Scheme jokes then. Does this work? Let's see. Oh, yeah, look at that. So I have a lot to talk about. So it's nice that it's a Lisp group, because I can also presume that you're all very smart and I can talk fast. So first I just want to set this up. What was I trying to do in building Clojure? Well, I wanted to have a Lisp. Okay, I fell in Lisp a long time ago and decided this is what I want to be able to do. In particular, I want Clojure to be a functional programming language, and there's a lot of reasons for that, one of which has to do with the robustness of programs, and the other of which has to do with concurrency, which we'll talk a lot about. I want it to be a language that supports concurrency. In what I do, I haven't written a non-concurrent program in almost 20 years. I do broadcast automation software and things like that, and there's always more than one thread or process. Clojure also is designed to run on the JVM. Being on the JVM is not an implementation detail. It's an objective. Interoperating with Java is an objective and an important part of Clojure. It's not just something under the hood. Which brings me to my next question. How many people know Java? Oh, good. Okay. I will make fun of Java. But I hope after this talk is done that you have an appreciation of the difference between the JVM and Java. It's okay to hate Java and like the JVM. That's where I'm at. Also, Clojure is open source, because I think that's mandatory for adoption for a language. So why Lisp? This is not an audience in which I have to justify why Lisp. Right, we all like Lisp. It's dynamic. In particular, for me, it was great because it's got a small core. The same, you implement these 7 primitives and just macros and everything else takes you from there, which means I have a shot at getting it correct. Unlike languages, which have all that syntax and then therefore very complicated compilers and parsers and everything else. We all like Lisp syntax. This is still an advantage of Lisp. Code is data, and the resulting macro system and syntactic abstraction. Also, I saw in Clojure an opportunity to help along the never-ending battle of having people not balk at the parentheses before they see the rest of the value. So one of the things I want to do, and one of the questions I expect to face in this room is, we have these 2 great Lisps. They're standardized to some degree. Why yet another Lisp? And I think this is an important and valid question, which I'm going to answer tonight. I think any new dialect of Lisp should be asked this question and should have a good answer. So some of the reasons why I couldn't use Common Lisp or Scheme for what I wanted to do was they're hard to change. I don't know how you change Common Lisp. Scheme just recently changed a little bit. Because I want a language that's functional, I want the core data structures to be immutable. Okay, that's not something you can retrofit on either of those 2 Lisps. There are no concurrency specs for those languages as they exist. That's not to say that implementations don't provide concurrency semantics for the stuff that's already in the language or facilities for dealing with threads, but it's not in the language. It's not something you can presume. It's not something that ports. And there are already good Lisps on the JVM. Kawa, Armbert, Cisc, they're all good. So if you have as your objective, I have all this code and I want to move it on the JVM for some reason, that's a solved problem. There's no reason for me to take it on. The other thing has to do with languages and platforms, and I'll talk more about that, but basically Lisps, like any language of their day, are kind of their own platforms. And that's also true of languages like Python and Ruby. So why the JVM? Well, it's coming around that just like you would say, I want this language and I want to target this operating system. I want to be able, I'll port it to these operating systems as targets. Virtual machines are targets. In fact, they are the new targets. They're the new platforms. Just like you would say, well, this is a platform, Unix is a platform. For businesses, these VMs are platforms because they abstract away platforms, or what we used to call platforms. The hardware, the instruction set, the CPUs. No one wants to deal with that. No one wants to deal with the OS level stuff anymore. So we've now got another layer of abstraction, which are these virtual machines. The two big ones are .NET and Java. And they provide a lot of facilities, more than just how do you access the file system, including type systems. What's interesting and surprising a little bit is that the type systems in these VMs are dynamic. They have dynamic enforcement, dynamic creation of types. They're very dynamic, even though the languages that typically target them, Java and C#, are not particularly dynamic. The big story, of course, is these huge sets of libraries you get to tap into, all this code that other people wrote. They also provide a bunch of high-level services like garbage collection and memory management, resource management, meaning that garbage collection is no longer a language problem. Garbage collection is a platform problem, which is good. And also, I'll talk more in detail about this later, but they offer bytecode in particular, and the JVM, just-in-time compilation that is extremely sophisticated. Runtime analysis and of your running program to find best paths, optimize short call paths. These things will take apart your code, make a fast path, compile a special fast path, all kinds of things that you absolutely cannot do with a static compiler. The compilation technology on the JVM is state-of-the-art. So old school was, well, we didn't have very great tools. We were all writing our languages or starting or bootstrapping with C. And every language sort of solved the same set of problems, defining its own platform, its own garbage collector, its own bytecode, its own type systems, and facilities for libraries. Now we can look to these VMs to provide that stuff for us. And in particular, they can provide it in a way that's somewhat independent of language. I wouldn't pretend that the JVM or the .NET runtime, the CLR, are really independent of language, especially the CLR. They talk so much about it. But really, any language can target this platform as long as it looks like C#. But it ends up that if you said, well, if I wanted to have an abstract machine, I could have like a little stack machine that did almost nothing. Or I could have a stack machine that had sort of a primitive object system. Well, that's what these virtual machines have. They have the primitive object systems that are supported by C# and Java. And a big thing for me is Clojure is designed to let me continue to work for a living. And I know a lot of people in this room, or some people in this room, are extremely lucky and can write Common Lisp for money. Great. But most people can't. Platforms are dictated by clients. Just like they say, I have this Sunbox and your program has to run on it. They also now say, I have this JVM infrastructure and your software has to run on it because my guys know how to install it, secure it, scale it, and you have to target it. If you don't, your language, it's just like your language didn't support OS 10. Your programs just couldn't run there. And they have real investments and they're not stupid. This is a real requirement in a lot of commercial software. So, again, as I said before, I'd like to hopefully get you to distinguish between Java and the JVM. Unfortunately, Sun called them both Java for the longest period of time. It was like Java the ecosystem and Java the language, which made it difficult to split them apart, but it's really always been the case. There are hundreds of languages that target the JVM. And now that the JVM is open source, you're seeing even more adoption and more targeting, more libraries, more infrastructure. Any language always had to have an interop layer with something. Typically that was C. It ends up that that's pretty insufficient because lots of the great new software and lots of the great new infrastructure is not being written in C. The old stuff was, but a lot of the new stuff isn't. So some ability to call or consume Java is critical, and it's very difficult to do with a bridge. I've written 2 bridges for Common Lisp. You may know of JFly or Foil. I wrote them. I tried very hard to make that work, but it's not a satisfying experience. So we look at Clojure as a language and the JVM as a platform. Why functional programming languages? Well, I think there are a couple of benefits before you even get to concurrency. They are certainly easier to reason about and easier to test. Now, everybody will say, Lisp invented functional programming. We've been doing functional programming from the beginning. It's certainly possible to adopt a functional programming style in Lisps that already exist. And that's both true and not true. It's true in that, yes, if you want to use lists only and you promise each other never to modify them, you can take a functional approach. But otherwise, you can't. And I'll talk more in detail about why that's the case. When you get to concurrency, however, you need to take a much more serious view of what it means to be functional and what it means to be immutable, because it's going to be the case that we simply cannot go into this multi-core environment and keep scribbling on the same memory from different threads. There aren't too many dynamic functional languages. Erlang is sort of a dynamic functional language, and Clojure is one, but most of the functional languages like Haskell ML couple this functional programming, and by that I mean programming without side effects, with these ornate and very complex type systems, because that's where the hot research is. But they don't need to go together, although people will dispute that. In particular, it's my opinion, having tried to get people to do it for a pretty long time, that functional by convention is not good enough, both because people mess it up and because it's not subject to the optimization that's available when things really, really are immutable. Something that's genuinely immutable and provably immutable by the optimizers is a different thing from something where two people have said in a conversation at lunch, I promise not to change that. All right, why focus on concurrency? Well, we've long since, I mean, it's been a while now, we are not going to have our single-threaded programs have their performance improved by time passing and Moore's law kicking in. That is over. We've hit this plateau. It is not going up. If you have a program right now today and it's only capable of running on one CPU, it will never, ever be faster. Okay? That wasn't always the case. It used to be you wrote a program, you said, man, by the time we finish this, it'll be fast enough. And that's not the case. So you really have to get a grip on this. But trying to do this with threads, with the conventional mechanisms, and Java has locks, and everybody has locks, and a lot of the languages, a lot of the enhancements to Lisp that support multi-threading really have the same kind of crusty, lock-based mechanisms for dealing with concurrency. They don't work. They're very, very hard to use. They don't scale, and even if you happen to get it right in one moment in time, in maintenance, it breaks. Programming in a functional way helps. Of course, anything that's really immutable, you don't have to worry about. Multiple threads can access it. There's no sweat. Nothing bad can happen. But it ends up that most real programs that do real work that people will pay for are not functions. The things that a lot of the functional programming guys write are really functions. A compiler is sort of a big function, right? It takes the source code as an input, calculates spits it on the disk. A theorem prover is sort of a function. A broadcast automation system is not a function. I work on the election system that runs on election night. I can tell you that's not a function. It's all we can do to make it function, but it's certainly not a function. So these kinds of real programs are more like models of processes. You go into a business, they have this process. Most things have to run indefinitely. So you need something that's going to appear to change over time that multiple parts of the program can access. We typically would call that state. And it's a reality. So Clojure couples this immutable approach to programming with some mechanisms for doing safe state. And in particular, I think it's critical that the language provides both support and enforcement for that. That it's not a convention, where locks are a convention. Clojure is not object-oriented. And there are many reasons, most of which have to do with the fact that I think we have to dig ourselves out of this rut we've gotten into with object-oriented programming, because we just haven't done anything novel with it in decades. But in particular, for this problem space, it's a disaster. Okay? Object-oriented programming, as normally implemented, is inherently imperative. It's about creating this object and banging on it from multiple threads. There's encapsulation, but it doesn't, that's orthogonal to the problem of concurrency. So this has got to change. Also, I think the traditional style object-oriented programming, where you have methods inside a class, has been proven not as flexible as Common Lisp generic functions, which show we should bring this polymorphism out of this box and apply it to multiple arguments, for instance. And I go even further and say, why do we base polymorphism on types alone? You know, in the real world, we don't categorize everything by a fundamental at-birth type. You know, nobody's born a taxi driver or a painter or tall. But, you know, these type systems work that way. You shall be tall, and we'll make every decision about you based upon your being tall. Whereas most systems and most reality supports some sort of polymorphism based upon value or current state or relationships to other things. So we need to sort of pull this stuff apart, and the traditional object orientation has just put us in this rut where we can't even see the difference between these things. So this is the question I want to answer in addition to others tonight. Why is Clojure different? The first thing that's different about Clojure is it has more first-class data structures. So Lisp, you know, if you interpreted Lisp as list processing, you know, there's definitely a primary data structure, which is the list. And everybody who uses Lisp, especially Common Lisp, knows that ain't enough, right? It's not a data structure that scales well. It's not suitable for a lot of application domains. And of course, Common Lisp has other data structures. It has vectors and it has hash tables. But they're not first class. Okay? There's no reader support. They don't print well. They just are not as nice as lists. So Clojure enhances Lisp by making print-read representations for more data structures, and I'll show you the details of that. Another big difference with Clojure is that the common and core algorithms are defined in terms of abstractions. As we'll see, a lot of the library in Lisps is based around a concrete data representation, you know, the two-cell cons. That is really bad. Of course, no one's blaming McCarthy for doing that 50 years ago. It was brilliant. But today, we can do better, and we have to do better. Clojure is different again because it embraces a host. It is symbiotic with the platform, which means it's going to get a lot of leverage of that platform and work other people have done. We're thread aware, and as you'll see, I am not constrained by backwards compatibility. I am not going to compile your old code. That's not the objective of Clojure. And that frees me up to, for instance, reuse words, which if they are to mean what they mean in Common Lisp and Scheme forever, you will never have a Lisp with different semantics. You just can't own the words. Sorry. Okay. So I'm going to break this down. You know, we're sort of branching like a tree. We'll talk about Clojure as a Lisp. We'll look at the data structures. I'll talk about abstraction and building algorithms on top of abstractions instead of concrete data structures. We'll dig into how the immutability works in Clojure. And then I'll look at some grab bag of Lisp features. So you'll see how Clojure differs from Lisp or Common Lisp or Scheme. And then we'll dig down into the concurrency mechanisms in Clojure. And finally look at the JVM, both how you interoperate with it and how is it as a host platform. So Clojure meets all the objectives of being a Lisp. It's dynamic. Code as data, which is a primary characteristic of Lisps, is the same in Clojure. It's the same compilation model as Common Lisp. I'm sort of a Common Lisp guy. I'm not a Scheme guy. So I like the reader and the properties of the reader being well defined. It has a small core. You have a REPL. It's lifted the notion of lists to this abstraction called sequences, and I'll talk a lot more about that. And it has macros and the other goodies you expect from a Lisp. If you use Clojure, you would not be at all confused about it being a Lisp. As a Lisp, these are the details. It's a Lisp 1. It's lexically scoped. It's a Lisp 1. However, it has Common Lisp style, sort of full function macros. Do whatever you want in there. And it has dynamic variables which behave a lot like dynamic variables in Common Lisp, except they have threading semantics. It's a case-sensitive language. That's really got to go. If you want to interoperate with XML and sort of anything, you have to be case-sensitive. It has namespaces instead of packages. And I might have some time to talk about that in detail. But in particular, it's important to note that Clojure's reader is side effect free, which is a big benefit. Clojure is 100% compiled. There's no interpreter. It loads code. It compiles it right away to JVM bytecode. From there, there's a lot more compilation that goes on, which I didn't have to write. As I said before, there's some very sophisticated optimizing compilers inside the JITs, inside Java VMs, in particular Hotspot. Clojure does not have tail call optimization, not because I'm against it. I'm all for it. It's something I had to trade off in being on the JVM. However, I was just at the JVM Languages Summit, and tail call optimization, every language designer who came up there said, tail call optimization, tail call optimization. They've heard it, and hopefully it will come in a future VM, hopefully soon. A lot of the names are different. As I said before, the names can't mean the same thing forever and ever and ever. There's only a few good names. So these are the primitives of Clojure. Fun is like lambda, if, def is define, let, loop and recur, I'll talk about it a little bit later. Do is block operation. New, dot are Java things, Java interop things. Try and throw have to do with exceptions. There's set, quote, and var, which I might have time to talk about. But this should be familiar in terms of their operation, if not the names. So the atomic data types are the things you would expect. Clojure has good math with integers that don't truncate or wrap. There are doubles. There are big decimal literals, which are important for people who deal with money. There are ratios. Strings are in double quotes. Characters are preceded by a slash, a backslash. There are symbols. The thing about symbols is they are not places with values stuck on them. Symbols and vars are different in Clojure. They're two separate things. So you can consider symbols in Clojure to be more simple names. There's no interning of the symbol with associated values. Keywords start with the colon. The colon doesn't participate in the package system like it would in Common Lisp. So there's no implication there other than the typical thing you expect of keywords, which is that they evaluate to themselves. There are Boolean literals, true and false. They unify with Java Boolean. And there's nil, which unifies with Java null. So Java null and nil are the same thing. I'll have a whole slide on nil, so I'll save the arguments and whatever for that. And there are regex literals, but there really aren't any more atomic literals than these. So I said earlier, Clojure has more first-class data structures, right? Everybody knows you couldn't write a performant program with lists. Okay, it's just going to be a pig. Yes, you can use a list and pretend you have an associative thing, but it's not good enough. The other ones are second class. They don't have reprint support. In particular, though, they're not very Lispy. A Lisp hash table is not Lispy at all. Okay, you can't recur on it. You can't build it up incrementally. You can't unroll the stack and just pop off values and use it like you do a list. You don't use hash tables like you do lists in Common Lisp, right? And same thing with vectors. And one of the reasons why is because they're destructive, right? You add something to a hash table, you've trashed it. You can't undo that trashing. Which means that you do nice things with lists, right? You make lists of A lists as you go down. If you're writing a little evaluator or a compiler, right? You'll have a list of A lists, and you can just unroll that and pop it right back off, right? Because it's all non-destructive. You can't do that same job with hash tables. In Clojure, you can, because Clojure's data structures are structurally recursive. You could say lists of A lists for an environment. That is really not so great. But I'd much rather have a stack of modifications to a non-destructive, true, performant, associative data structure. And that's what Clojure gives you. In particular, compared to the languages du jour, Python, Ruby, whatever, the lack of a first-class associative data structure is really a bad blight on Lisp. People look at that and they're like, I can't even work with this. Because it's something you really need. So Clojure has it. So what have we got? We have lists. Okay? We have lists, they're singly linked, they're exactly like what you know. I've heard rumors Clojure doesn't have con cells. Clojure does have con cells. What Clojure doesn't have is a giant, beautiful library that's married to con cells. That's what it doesn't have. It does have con cells. Clojure has vectors, it has maps, both hashed and sorted. By maps, I mean associative data structures, hash tables. A hashed map is a hash table. It has sets. Again, first-class sets, both hashed and sorted. They all have read-print support. They're all structurally recursive. In addition, they all support a uniform add operation, which is conj, another SJ pun. But it ends up being an extremely powerful thing. You can write algorithms that manipulate lists, vectors, maps, or sets uniformly. Add things to them, look for things, map functions across them, and you could just substitute a map for a set, for a list, for a vector, not change the rest of your code at all. Okay, so if you have this presumption that, oh, you have these data types, more data types means more complexity for my macros, and I have all this gook because now I have this heterogeneity to my data structure set. That's not true because you have homogeneity in your algorithm set. And I'll show you more about that later. And conj is one of the keys to that. This is what they look like. Lists look like what you're familiar with. Okay, it's just parenthesized. They're heterogeneous. You can stick anything you want in there. They grow at the front. Every time I say grow, change, add, remove, there's quotes around it. Okay, because none of these things actually change. So, just like a list in any of the lists, adding something to the list doesn't change the list. It's a new list, right? That logic applies to all the data structures in Clojure. Vectors support fast indexed access, like you expect. They also grow at the end automatically. So you can conj onto a vector and it's going to grow at the tail. Maps are in curly braces. It's just key value, key value. Commas are white space. They make people coming from other languages feel more comfortable, and so they can use them, and we don't care. If you don't want to use them, you don't have to. So commas are just ignored. And again, it's key value, and the keys and the values can be anything. Sets are in curly braces preceded by the hash sign, and that's just going to be a set of unique things. Okay, but to support fast lookup and detection of the things in there. And they have, as I said before, both of these sets of maps have hashed versions and sorted versions with different performance characteristics and sorting characteristics. And then all of this stuff nests. So this is just some code that uses the data structure literals, and you can see what's going on. So you can just put the literals in your code, and you get versions of that. Of course, as in all lists by default get evaluated. So if you want a list, you have to say list or record it. But the nice thing is we have this uniform interface. We can add to any collection something, and it will do the right thing for whatever kind of collection it is. So we can add key value pairs to maps. We can add to the beginning of the beginning of lists and the end of vectors. Making these changes doesn't really change anything. When we see reprint, we get the changed versions and then the unchanged versions. If at any point somebody has questions, just shoot.
Well, what does that program do?
This program just shows you it does nothing. It creates a vector, a map, and a list. It adds something to each of those, and it's returning a vector of the changed versions and the original versions.
Oh, the brackets are... Yeah,
it's a literal vector, right. So it's a vector of the answers and the originals.
Okay.
And then we get a vector of the answers, changed vector, changed map, changed list, and the originals, unchanged original vector, map, and list.
Right there, got it.
Yes?
Are commas white space everywhere, or just within maps and...
Everywhere.
All right.
Have at it. Stick them anywhere you want. Just whatever makes you feel good.
Is the square bracket the only way to make a vector?
No, there are functions for all these things. They're named functions for all of them. So you can map, vector and get vectors.
Is the bracket part of the let syntax then?
Yes, the bracket is part of the let syntax. You've seen some schemes start to advocate using square brackets for lists that are not calls, right? And in them, like PLT or whatever, they treat them as lists. That same convention of using square brackets when things are not calls or operators happens in Clojure. So these are not calls. So people don't get confused because when they see parens everywhere, they're like, is this a call? Is this data? I can't get my head around it. So that convention was a good one, except in Clojure, I don't want to waste square brackets on another kind of list. So I have real vectors.
So that is like in the actual code of data that comes.
That's a vector. When this is read, this is a list with a symbol, a vector with a symbol, a vector, symbol, map, symbol, list, vector, et cetera, et cetera, et cetera. This is real code as data. You read this in, it's fine.
But, and it could have been, you could have equally been a hash table when you use the map.
This is a hash table.
Not as the first type of the map.
Oh, that's the destructuring stuff. I'll show you that later.
Speaking of all the syntax and products data, how does the comment and deal into the, does the comment parse into the
Ignored.
like that? So-
Ignored. It's the old ignored. Ignored to the end of line comment. So reader, nothing is produced by the reader for that. It's a cool reader, though. For instance, it captures all the line numbers and associates them with the data structures as metadata. I'll talk about metadata later. Okay? So this is a big thing I want to talk about, and I want to kind of beat up on the existing lists. Not because they made the choice, but it's a choice that's getting moldy. Okay? Which is, you have so many great algorithms defined in terms of concrete data types. Right? That's really a mistake today. Right? It limits how general your code can be. It limits the extensibility of your language. How many people said, oh, I wish this was a generic function about some library function? Right? Okay. So yeah, you do. Because the generic functions are the abstraction mechanism in Common Lisp, and they weren't used a lot in the standard library because of the way the history was. Again, I'm not blaming the people who wrote Lisp, Common Lisp and Scheme for doing what they did. It's just today, starting from scratch, that would be not a good idea. Because there are so many efficient mechanisms for implementing abstractions that are fast, that are super optimized. It ends up on the JVM. That mechanism is interfaces and virtual function calls. So under the hood, implementing this stuff, implementing these abstractions in terms of that mechanism means it's super fast. Right? Because some people say, well, we can't make that thing in Common Lisp a generic function because we just can't take the hit. No hit. These things, I mean, these optimizers can make them all go away in inline virtual functions pretty much everywhere. So this happened a lot in Clojure, but I want to take as an example case the console, getting rid of the console, getting it out of the library code. So the console is just brimming with details, right? It's so sad to see the Lisp books, with a pair of boxes with arrows between the boxes. What a horrible way to start, right? Because there's a great abstraction that's in there, that's inside conses, right? We don't care that it has 2 slots. Well, we don't care about car and cutter at all. We don't care about the contents, and in particular, we don't want to know that at all. I don't want to promise that you're going to give me back something that I can change. That's terrible. So if we were to lift the interaction pattern you have with these things, there's only 2 things, right? Get me the first thing, and get me the rest. 2 functions. 2 functions that have nothing to do with pairs, with consoles, with boxes, or arrows, right? This is an abstraction in there, which is, there's this sequence potentially. Now, what if there's no sequence? What do we have? Well, the Common Lispers will say, you have nil, right? And I do too, okay? But nil means nothing in Clojure. It means you have nothing. It does not mean some magic name that also means the empty list, okay? Because there's empty vectors and there's empty all kinds of things. Nil means you don't have something. So either you have a sequence or you have nothing, nil. If you have a sequence, it's going to support these 2 functions. First is going to do what? Return the first thing in the sequence. That's good. Not surprising. Rest is going to do what? It's going to return another sequence. Okay? Again, no change. This is not an iterator. Right? This is the abstraction inside consoles. Right? Rest says, get me the rest, which is going to be either what? A sequence or nil. That's it. That's the abstraction that's inside there.
So no
What's-
improper laces?
What?
No improper laces?
No.
No dotted laces? Okay.
Well, at this point, I've stopped talking about lists, right?
Right, fair enough.
I have nothing to do with this. In fact, the next thing I'm going to say is there's no reason you can't build an exemplar of this abstraction on top of vectors, right? I can make something that implements first and rest on vectors. I can implement something that implements first and rest on maps. I can implement something that provides first and rest on anything. And that's what happens. All the data structures in Clojure support a function called seek, which gets you something that implements this interface on that data structure. Now you've got this separation of concerns. Sequencing across a data structure and the data structure are separate. So we've lifted that away. That is a big deal.
Wait, what does seek do if you give it a vector?
It returns something that implements this interface on top of the vector.
Cursor.
You could consider it a cursor if you want, as long as you don't associate that with anything like iterators in these broken languages. It's not a stateful thing. It's literally this. What's the difference between rest and move next?
That just gives you the rest.
Rest gives you another thing, right? Move next is a cursor. It's destructive on the iterator. Iterators are bad, right? Sequences and this abstraction is good. Because it means, for instance, with an iterator, you can't like look at three things and then hand the head again to somebody else. That head, that's toast. You moved it. You can't even get at it anymore. That's not true with these. Okay. So when you say to a vector, give me a seek on you, you get a new thing. It's not the vector. Of course, some things can implement rest, first and rest themselves. What can? Actual list. What a beautiful thing. So when you implement this thing on consoles, they are non-allocating exactly beautiful, the same exact stuff you used to have. It's just we've separated this from that. But that is still the most efficient implementation of this.
So the seek on the left can turn the left. Or does it-
Yes, it does. So this is a famous quote, and it's a good idea. We have to go further now. Okay? We should be implementing our functions or our algorithms on top of abstractions, not data structures. Pull out the abstraction. Seek is implemented for everything in Clojure. In addition, I implemented seek on almost everything in Java. Java collections, any Java iterable, Java strings, Java regex matches, lines from a file, et cetera, et cetera, et cetera. There's a seek implementation for all of those, which means that all of the algorithms in Clojure work on everything.
Do you have any trouble with the object overhead?
No. No, certainly. Right. Let's just take an example. Vector.
It's pretty huge in Java.
No, it isn't.
The JVM.
No, I disagree. I disagree strongly. No. No. No, we have to stop doing this. We have to stop doing this right now. I'll tell you, I'll have an anecdote, which I'll use a couple of times because it was extremely cool. I was just at the JVM Languages Summit, where there was a guy there who works for Azul Systems. This is a company that makes these mega boxes that run Java. They're dedicated to running Java. They have hundreds of cores. I gave him this little Clojure program I wrote in an afternoon. It's less than 100 lines. It implements an ant colony optimization of the traveling salesman problem. I only had a 4-core machine. I did what I had to, and I used some of the stuff I'm going to show you later, the STM and the agent system. But he said, oh, I want to try it on my thing. So he tried it on his thing. And boom, he pulled up my program. It ran on 600 cores. Boom! Just like that. He had these cool tools for watching the cores with LED graphs popping up and down. It was so exciting. And that program was churning. You know how much it was churning? It was churning 20 gigs of garbage a second. 20 gigs of garbage a second. You know how much of the overall CPU energy that used? 7%. Guess what? Ephemeral garbage on the JVM is cheap. And that is a design principle underlying Clojure. Okay? Because you can't implement seek on a vector without allocating memory. Right? What is a seek on a vector going to be? It's going to be a thing that has an index in it, right? And when you ask for the next, for the rest, what's it going to do? Make a new one of those with the index that's one greater than that. That's going to be an allocation. So there are many data structures you can't sequence over without an allocation per step. That's a beautiful thing. You have to see the way these JVMs optimize that stuff away. You cannot be concerned about ephemeral consing anymore. It's a real design misfeature to prioritize that. The other key thing which we'll see in Clojure is first and rest. They are so lightweight concepts that we don't actually have to have a sequence, do we? How much of a sequence do we need to implement first and rest? One thing and some way to get at the other things. Almost nothing. Right? We don't have to have a realized sequence or a realized data structure at all, do we? So it means that we can implement first and rest lazily. That ends up being an extremely powerful part of Clojure, leveraging that. So let's look some more. So that's, yes?
I'm sorry. On the last slide, you implemented seek over Java collections.
Yes.
And playing around with the seven. I didn't play around with it enough to find out the answers. You lose some of the immutability guarantees when you start iterating over collections. Right?
No, you do not. You do not lose the immutability guarantees of the sequence. Right? The sequence, as it walks across the collection, caches everything it finds. So if you've made a pass, you will never get different answers. If you've made that sequence on top of some crappy mutable Java thing, and you've mutated that thing for multiple threads, you're going to get the normal Java error from that, which is concurrent modification exception. Okay, but no, these seeks, they are immutable. Right? They're golden. You walk through, you get the same stuff. You can share it. You can share it between threads. You can point at different parts of it. No, really. Okay, so I've just shown you one, right? The sequence, we sort of broke that down. But there is a similar abstraction behind all the associative things, the associative maps, and the index vectors, and the sets. When I showed you those pictures of those literals, well, there's a bunch of implementations of these abstractions. Right? One of the neat thing about having a data structure that returns a changed version of itself is you can have one type for when it's a tiny hash. And then as you add stuff to it, one of those adds could return a whole different type that's optimized for being slightly larger. And then when it gets bigger than that, one of those adds can give you yet another different type for being huge. All that stuff happens under the hood in Clojure. So the key thing is that we're working with abstractions and not any promises of the concrete type.
Actually, to add on to that, you said that the numbers are also the speed rate, they don't overflow.
Yes.
And that's the same sort of trick. So you don't have intermediates, they're all boxed all the time.
Yes, numbers are always boxed all the time, but I'm going to accept when they're not. Which I have slides for, so I'll talk about that. So all the data structures have corresponding abstractions. Callability itself is an abstraction. Okay? There's no reason to say only lambdas, can be called, and the Lisp 2 thing of the thing in the first position is going to be hardwired to be this type of thing. Callability is an abstraction, and it's implemented by several of the data structures. Okay? Maps are functions of their keys. Well, guess what? It's because a map really is a function of a key, isn't it? That's what it means to be associative. It's a function. Right? So maps are functions, vectors are functions, and sets are functions of their keys. Because that's really what it should be. There are many implementations, as I said, and the cool thing is, this is an infrastructure. I've given you the interfaces for these things. You can extend this yourself. You don't have to call me up, say, oh, I wish you had this kind of cool data structure. Could you please add it? You can do that. You can do that from Java or from Clojure. Anybody can do it. And all the algorithms you have, and all the algorithms I've already written, and all the algorithms all the other people have already written, are going to work with your new data structure without change. Okay, that's the power of abstraction. You get a large library, and by building, F functions and I implementations, you get F times I power.
Quick question. You
Yes.
said that, return when you say call rest or add something to a function, you return a different object. Right?
Yes.
How does that affect inlining?
How does it affect inlining?
Because earlier you said we didn't have to worry about this stuff because it all got compiled away under the hood.
Right. If you were concerned about it affecting inlining, it would be because you were working with the biggest ones. And so that optimization is going to kick in after a number of times. For instance, the JIT in Java will typically watch your function and say, you know, you're calling this a lot. I'm going to go set off a thread on the side and try to figure out how to do that fast. By the time you're doing that, you're already on the big ones, typically. You're either already on the big ones, you're already on the big size, or you will always be on the small size. In other words, you're not doing something that's really growing it. But yes, that kind of polymorphism does impact inlining, and that's an ongoing challenge for the JIT guys to do. All I can say is they're doing it better than anyone ever has so far. These compilers are amazing. Okay, so let's talk a little bit about laziness, because it's another key component of the way Clojure works, right? Which the basis of it is very simple. First and rest are not produced until requested, right? How much of a list do we need to have? It ends up none at all. We just need a recipe for finding the first thing and a recipe for finding the rest of the things. That is really all we need to say we have a sequence. So there's an easy way to define your own lazy sequence producing functions. It's called lazy cons. It takes two expressions. It's a macro. It takes two expressions. One will produce the first value when requested. The other will produce the rest. Okay? Everybody's now going to raise their hand and say, oh, we've had lazy streams. We know about lazy streams. We have it, whatever. But all the lazy streams libraries, right, do they interoperate with the concells? No. There's lazy this and lazy that and lazy map and lazy whatever and lazy whatever, and you can't cons or whatever. That is not the same. Okay? If you have first and rest, you're a seek. You can cons concrete things onto lazy things, and then more concrete things. And you can concatenate them all. They are all the same from an interface perspective. It's not the same thing as a lazy streams library. Although you can understand lazy cons by understanding the way lazy streams work in libraries like the ones for Scheme. You can use them like iterators or generators of other languages, but they're much better because they're not mutable. And the interoperator I already said. So this is what take looks like. Take is kind of more Haskell-ish lingo. Take in things from some collection, right? If it's still a positive number, and there's stuff in the collection, okay? This is classic Lisp punning. You know, there's a cons or there isn't. Yes?
So you're going to tell me later how to write a take that actually returns the value of an arbitrary type? Because here you're writing a take and it returns a sequence.
Take returns a sequence.
It returns a sequence.
It returns anything that implements seek. Seek is an abstraction, so it can return any arbitrary type that implements seek. Not one particular type. Seek is an interface, so that doesn't dictate the concrete type. It only says whatever the concrete type is, it has to support this interface.
Yeah, but what I get back is going to be a seek.
An implementation of iSeek. Yes. So that's pretty cool. So we just lazy cons, calling first on that, and then taking on the rest. Okay? Yes?
So if I wanted to take the first 100 things out of a vector and have that be something I can random access, I would want to use this function.
Well, no, you can take it and then you could dump it into a vector if you wanted to. Or you can use subvector, which is a constant time way to get a window on another vector. If you really want another vector with constant time lookup of size.
So there is still a difference in that sense.
Yeah, I mean, yes, the sequence library is still a library of sequences. It has the properties of sequences, which is, linear access. But there's so many things you do with that, mapping and filtering and all those great Lisp functions now apply to everything. That's the point. It doesn't make sequences now the best data structure for all usages. Sometimes you're going to take that thing, and because you need to hammer on it from a lookup perspective, dump it into something where that lookup is going to be fast, because it's not going to be fast on a seek. But that's very, very easy to do. Any other questions on this? Okay. So as I said before, Clojure is primarily a functional language. There was a great talk by Eric Meyer where he said we were all wrong about functional languages. The only possible functional language is Haskell. Because it has to be lazy and it has to have this type system, and the type system has to let you declare effects, et cetera, et cetera, et cetera. The rest of us sort of banded together and said, well, we still want to call our things functional, but we'll put this qualifier on it at all times. So So it is impure. It certainly is. I don't believe in disallowing dangerous things because, sometimes dangerous things are useful. The idea behind Clojure is it gives you tools to do the right thing, and if you can do that most of the time, your program will be a better program. If you have to do something ugly somewhere, I'm not going to stop you. I know you have to do that, either for performance or whatever. So what does that mean for Clojure? For Clojure, it means the core data structures are immutable. The core library functions do not produce side effects. Left-bound locals are immutable, so no even twiddling inside your function. Because if you could, you'd have all kinds of other issues, because you could close over those twiddleable locals, and then et cetera, et cetera. Also, it creates this awful style, right, where in the whole world, you're doing this nice thing with functions and applying functions, and then inside your functions, you have this mess where you have, loops that trash local variables, and you just end up making spaghetti, little small bowls of spaghetti. So we don't do that. Because of the lack of tail calls and the desire to have a sort of a functional way of programming, I needed a special construct for looping, which I'll show you. So this is sort of what it looks like to use. Right? Drop two things from the vector, you get a sequence of that. Infinite sequences, why not? Right? Cycle returns an infinite sequence of looping through whatever it was passed, over and over and over again. As long as you don't try to print it at the REPL, because I haven't implemented print length, you'll be fine. But that is really a beautiful thing. It will change the way you write software to have essentially all of these functions are lazy. They all return a lazy sequence. All of the algorithms in Clojure that can. I mean, some things can't be lazy, but anything that can be lazy is. So if you pass some huge, humongo thing, partition 3 is going to return just a window on getting the first one. It ends up that makes it really easy in Clojure to manipulate and work on data sets that don't fit in memory. Also, you've been paying a huge price, right, by building your algorithms in terms of functions that return fully realized lists. And then, of course, n-reversing them or reversing them. It's awful. And from a memory contention standpoint, it's a big deal. Remember I talked about that ephemeral memory being cheap. You know what else is really good? Ephemeral memory always lives in the generation that could get tossed for almost nothing, right? Garbage acquisition or memory acquisition in that generation is pointer bumping. And the collects are extremely fast. But when you start allocating real lists or real data structures to accommodate interim values, interim results, pieces of your algorithm are creating these huge things. Guess what? They're going to move into the next generation, and the garbage collection cost will be much higher than if you used a lazy approach. So this is really great. Interleave is lazy. These are all lazy. And this is just there's tons of functions in Clojure.
Is the first line a typo because you dropped a vector and got the list back?
No, you always get a sequence back from these. These are the sequence functions. They'll take anything, but they'll return a sequence. Because they're returning a lazy sequence. If I had to return a vector, I'd have to realize it, and then all the problems I just talked about would happen. If you want a vector, it's really easy to say, you can just say, into an empty vector, drop whatever, and now you'll have it poured in. In fact, into works with anything. You could say into a set, empty set, or a set that has some stuff in it already. So it's really beautiful. You can say into something, take blah, and it'll get dumped into the thing, whatever its concrete type is. So this is really neat, and it works on strings, and it works on whatever. Range is also a lazy producer. Infinite lists, infinite sequences.
Into is just a representation.
Excuse me?
Into is just a representation.
Into takes any type of collection, which is going to support conj, and then some sequence, and it will take the things from the sequence and conj them into the collection. So it will do the right thing for the type.
And then it returns the collection.
It returns the collection, that's right. So for instance, you can write a completely generic map, right? Because people say, oh, I wish you had map vector, right? Well, if you said into an empty vector, map this thing, you would get that. So then what's different between different calls to that? Just the thing, right? Just the, I'm dumping into a vector and I started with a vector, or I'm dumping into a set and I had a set, or dumping into a map and I had a map. Well, there's a function called empty. So if you had some collection called C, you could say into empty C, map this function on C. And whatever C is, you'll get a copy of it. And that code is 100% generic. You don't care, it will work on anything. That's cool. Okay, so this is some of what maps and sets look like. This is def, which just creates a global thing called M, right? And we give it a map. Maps are functions of their keys, so we can look something up by just calling the map itself. Also, keywords are functions. Keywords are functions of associative things. They look themselves up in the thing because keywords are so often used as names, as keys. So it ends up supporting a really nice looking style. And if you ever wished you had a better way to do attributes, this makes that nice looking. You can get the keys, you can get the values, you can do like all kinds of stuff. The basic operation for adding to an associative thing is assoc, which is that's short for associate. Again, you can't own this word. So it takes some associative thing and then an arbitrary number of keys, values, right? And it gives you a new map with those entries made to it. If we look at M again, it'll be the same thing that was there. In fact, this function, this call here, presumes M is the same way as it was because it didn't change here. So merge with is a very cool thing. It will take one or more maps, and it will say, pour all this stuff from these successive maps into the baseline map. Okay, well, what if there's already a key there? Well, use this function to arbitrate the value combination. So if there's already a key, take the value you have at this key and add it. But you can merge with conj and build data structures this way. It's fun. There's a whole library for set logic that works on real sets. Union, intersection, and all that stuff. And go a higher level still. What's a relation? A relation is a set of maps. And guess what? If you build relations, there's a whole library of stuff for that, like relational algebra stuff, like joins.
When you get that union there, what determines the order of the new union?
Because these are hash sets, the order is random, because it's hash. If they were sorted, you'd get a sorted thing. All of the literals are the hash versions, just so you know. The literal map is a hash map. The literal set is a hash set. But you can get the sorted versions with function calls.
And that line of associate could have written that with conj, right?
I could have written it with conj, but then you have to treat each guy as a pair, right? The values in a collection that is associative are pairs, logically. So like if you seek on M, you're going to get a set of key value little vectors.
Sorry, you said that it's because of the hash map, it's arbitrary order
In the print, right.
If I union two things that are twice, do I necessarily get the same thing? Or
You get whatever you started with. You're going to get whatever the left one is.
suppose I union these guys and then
Yes.
union them again.
Yeah.
I guarantee that the results will be the same.
You're going to guarantee the results are going to be equal. I'm going to talk about equal.
When you say that the reader versions are hashed, you don't mean that they're implemented literally with hashing, you mean that they're unordered?
I mean that the concrete thing you get is the hash map or the hash set. I have to pick one. I'm reading and I see a literal map, right? I have to produce a real data structure.
Yeah.
The real data structure I'm going to produce is going to be in the hashed family, not the sorted family.
Right. The point is that it has unsorted semantics.
I'm not going to promise what they are, but usually hash things don't have any sorting, right? Because maybe I'll come up with a new hash sorted hybrid. I don't know.
But you're not promising that it will actually really be a hash table underneath if it's small enough that you want it to be something.
Sometimes the fastest way to implement the hash is just to do a skip list thing, right? It's proven when it gets small enough. Yeah, but it's still in the hash family in that when that thing grows, it'll become hashed. I should make a slide of that. There's this huge, beautiful hierarchy of abstractions under Clojure. Somebody made a picture of it once. It's scary. So, for instance, there's an abstraction called sorted, and one called associative, which aren't even in the concrete tree of things, and indexed and reversible and stuff like that. The abstraction set is good. So, just to get a feel, again, I don't expect you to totally be able to grok Clojure code, but just to get a feel for the weight of it, this is some Python. Peter Norvig wrote this Python code. It's a simple spell corrector. It uses a little simple Bayesian thingy. But Python is sort of the champ in terms of syntactic concision, because it has no grouping, right? It uses white space, so and length. And so this is the Clojure version of the same thing, right? Roughly the same, and we all know how to ignore this. As do our editors. In fact, we know the superiority about being able to move these pieces around versus something that's white space based. Okay. So it's kind of neat. I mean, deaf and blind. You see, again, where we're using lists for where we would have used lists for data, we're going to use vectors instead in the syntax. There's list comprehensions or sequence comprehensions, a bunch of other cool stuff. But it lets you write code that's the same size and weight as Python. So saying that everything's immutable, usually the first thing is, oh my God, that is going to be slow. You're going to be copying those things left and right. But of course, that need not be the case. We know, for instance, that when you add something to a list, we don't copy the whole list. We don't need to because it has structural sharing. And similarly, there are structurally shared versions of these data structures. So by persistent data structure here, we're not talking about the database persistence, right? We're talking about the concept of having something that's immutable, be subject to change, having the old version and the new version both be available after the change with the same performance characteristics as before. So this isn't a trick one. There are some persistent algorithms that produce changed versions whose performance degrades over time as you have more new things. Older versions start slipping out from the performance profile. To me, that's not really persistence at all. And it's not usable. In particular, the way those things are implemented is usually with some real sharing, which means that they're a disaster from a concurrency standpoint. Really, to do this correctly, you have to have immutable data structures, which Clojure does. The new versions are not full copies, so there's structural sharing. This really is the Lisp way. This is the kind of map, or hash table, or vector you should have in Lisp, because you want to do the same kinds of programming with these other data structures that you do with lists. And so often you have this beautiful thing you did with lists, right? Then you try to scale it up and, lists are really not the right thing. Then what do? Completely change your program, right? Because using the other data structures is nothing like using lists. They don't have the same properties. They mutate, et cetera, et cetera. That's not true in Clojure. So you can use real maps for things like environments, which is just so beautiful and very, very fast. I don't have the slides for that. So I will say Clojure's data structures are the fastest persistent data structures I know about. They're different. They're based around Bagwell's hash map trees. They have a depth of log 32n, so they're very shallow, and they're fast. They're fast enough to use this for commercial development. Compared to the Java data structures, they're for insertion times, like 4 times worse. And for lookup times, they can be as good or better to twice as slow. So that's way in the ballpark, considering the benefits. And when you start comparing them to having to lock those other things in concurrent scenarios, there's no contest. So this is a small cost we're going to pay, and we're just going to be able to sleep from then on. All right. So as I said before, we have 2 things impacting Clojure from the looping perspective. One is, I don't want any mutable locals. The other is, the JVM won't let me do tail calls. Okay. You've seen languages, Sys scheme does tail calls on the JVM, right? It does it with this whole other infrastructure. Their calling scheme is nothing like Java's, right? You have to pass additional things, or trampoline, or whatever. Clojure does none of that. Clojure has pedal-to-the-metal calling conventions that match Java's. So I don't have tail recursion because you can't do that unless the JVM does that. So we have a special construct called recur. It does constant space recursive looping. Right? It's going to rebind and jump to the nearest loop, which is another special op, or function frame. So you say, I want to zip map this thing. I say loop. It's exactly like let. Right? Loop is like let. You let all these things, and then if we need to keep going, we recur. Recur is going to go and hit this loop, rebinding map K and V to this, that, and that.
So it does, so the Clojure compiler analyzes it, make sure it's a tail call.
Recur can only occur in the tail position, right? And I will flag you on that. Right. And it's a go-to. It's fast, under the hood. But the semantics are the semantics of rebinding.
What's going to happen though is if the JVM actually gets
Well, this recur happens to target this, but you can have recurs that target the function arguments themselves if there was no enclosing loop. So those recurs could be like a call to the same named function. But the biggest reason for true tail call is that you want to build some sort of network of recursive calls, not self calls. And basically what will happen is you can start doing that. Right now, if you do it, you're subject to stack overflow. And when they change this, you won't be. It ends up that in Clojure, because of the lazy sequences and this loop recur, people complain a lot before they start using Clojure, and they complain hardly at all after they know how to do it the Clojure way. That's not to say I don't want tail calls. I absolutely do, and I'm looking forward to the JVM guys doing it. But that's what I have. So that's a little zip map, and you can create, a set of keys and values, and they'll get zipped together and you get a map out. These two things would do the same thing. Just some more, you have apply, you can do that, interleave, or you could dump into that into I was talking about before.
I assume that if you wrote the code using a self invocation, you wouldn't attempt to detect that and then do something like this?
I don't on purpose, because I get a lot of people coming to Clojure from Scheme. And I really feel like I don't want to tease you. And I don't want you to be confused about when you will get a real tail call. Because I think that's an unworkable position to be in. Can I do this? Will I get a tail call? So I just say, no, you will not. The only time you will is if you do this. When we have tail calls, you can do the other. And that's really sort of clean. Because otherwise people would be very frustrated, and understandably. So I do not optimize self calls, even though I easily could. Okay, equality. The equal sign is equality in Clojure. There is also identical, which is reference equality. We really don't do that. It's there. I know sometimes you need to do it, but it's not something you're going to do often in Clojure.
consider it separate operator from the equality versus you don't call it.
Equal. Equal. Have you read Henry Baker's great paper on equality and object identity? Anybody?
It would have been a while ago.
It's a great paper. It's still great, and it's still correct. In it, he says, the only things you can really compare for equality are immutable things. Because if you compare two things for equality that are mutable and never say true, and they're ever not the same thing, you are wrong. Or you will become wrong at some point in the future. So he had this new operator he called egal. He went through all of this equal and EQ and EQL, and I need a new name. So he came up with egal and defined these semantics for egal. Those are the semantics of Clojure. Okay, if you're comparing two reference types, they have to be the same thing in order for them to be equal. Again, here I mean Clojure's stuff. There is still Java stuff. Java stuff has plenty of broken equals, and I can't fix them. So if you call equal on some Java things, it's going to map to equals, and it will be broken sometimes because they're broken. Yes, object.equals. I can't fix that. Use Clojure's data structures, they're much better.
For cyclic structures, do you do the thing about considering two things that are observationally equivalent, even if they might have distinct, you know what I'm referring to here?
Well, good luck trying to make a cyclic data structure out of all these immutable parts.
No, you don't, so you can't express.
Well, this cycle, which is not really a data structure, right? It's a logical sequence. I don't have any special tests for equality termination there, because I don't think.
Recently I just skied, so I was curious if you followed there's all the lead there.
No, I haven't yet. Don't do that.
But if you call equals on a lazy generator that generates an infinite sequence, what happens?
It's the same as trying to print it at the REPL. You're going to consume it all. That's right. I mean, it may terminate early. No, not abnormally, but it may terminate early because it'll find that things are not equal.
Yeah.
Right. If one is finite, it's finite.
Yeah.
What if you into and cycle?
Same thing. I mean, cycle is infinite. What do you expect? Take from cycle and build what you want. You don't get. There's no other infinite data structures. There are infinite sequences. There aren't infinite vectors or infinite maps. Okay, so that's how it works. I haven't even talked about references, but Clojure does have some reference types. They're the things that have those concurrency semantics. All right, the big religious debate. Nil, false, end of stream, or end of sequence, or end of list, and the empty list. Okay, let's just do it. Clojure has nil. Nil means nothing. You don't have anything. It's not the name of some magic thing. It means nothing. Common Lisp has nil and the empty list, and those notions are unified. It might have made sense because you really only had one primary aggregate data structure. I don't, right? Why should nil be the empty list? Why shouldn't it be the empty vector or the empty whatever? There's no good reason. Scheme punts on this. They don't like that nil punting or end of stream, end of sequence stuff. And Java has null, and it means nothing in Java. Could be any type. Clojure has real, true, and false. Common Lisp has nil or not, right? Scheme has true and false, but they're broken, right? And Java has true and false. Clojure's conditional logic is like Common Lisp's. I like that. I like nil punting. I like saying nothing is conditional false. So, but I have two cases because I have to deal with false. I have to deal with false. False is in Java land. It's going to come. I'm going to encounter it. I tried very hard. There's no way to automatically or automagically do a nil false translation in both directions. It's not possible. If you think it is, write it up and send it to me. But I think it's not. So I have these two things or everything else, which is like Common Lisp. It's also like schemes. Of course, this seems to be inherently wrong. You know, if you're going to do this, then do it. Right.
What's your objection to false?
I don't have an objection to false. I have an objection to if you're going to say true and false and this is logical false, well, no, it's not logical
I know,
false.
earlier, you said you forced to use false because Java uses false.
Well, I mean, it would be nice if I didn't have to do both of these. It would be nice if I could do nil and everything else. I would be happy with true and nil. I'm fine with Common Lisp's use of T and nil. That would have been done. I tried to make that work. Okay, is there a special singleton empty list? And the singleton is the key thing. There are empty list values in Clojure. In fact, they are not nothing. Because an empty list is not nothing. It's an empty list. And it needs to be distinguishable from an empty vector. Because you want to say into it. Right? If you only had nil, you have no power to have more than one special empty thing. So no. Clojure, no. We know Common Lisp and Scheme have the empty list. Here again, yes? You can have metadata on an empty thing. You can tell the difference between an empty thing and nothing. Because they're not the same. An empty bucket is not no bucket.
I'm not getting the distinction. Common Lisp has a specific empty list. Clojure doesn't have an empty list?
It doesn't have a singleton empty list. You can have 10 different ones whose identity differs.
Oh.
Okay, and it's not represented by nil. That's also sort of the key piece here. I'm not actually trying to establish the rightness or wrongness of anything except this. Just showing you how they're different, and the decisions I made, which generally, as you'll see through this, correspond to Common Lisp choices. And yes?
If all of those empty lists are immutable,
Yes.
then why would you not just have them all actually
I do. Why would I do otherwise?
I thought you just said that each of those empty lists had a different identity.
It could. It could, but I don't want to I don't want you to start doing identity stuff with that. That's not use equals. Okay, equals is good. End of sequence. Okay, what happens when we're using a sequence? It used to be a list. We're walking through and there's no more. Okay, well, I say nil as Common Lisp did because Common Lisp meant this when it said no more. I mean there's no more. There's nothing. So that's the same. And of course, combined with this, it means you can do nice, elegant little loop things. Because that idiom of Common Lisp is good. I have host issues. I have to deal with the host. So nil maps to null, true and false map to big T, big F, true and false in the Java land. And the library does not use concrete types. Are we okay? All right, that's easy. Okay, so this is just some sort of Clojure-y, how does Clojure do some things that other languages do, other Lisps do. Clojure can have arity overloaded functions. Okay, Clojure doesn't have optional arguments. Instead, it has real arity overloading. That means that a single function object can hold inside it multiple function bodies overloaded by arity. That is really fast in Java, and it's quite nice, and it means you can report all kinds of things, and you don't really have any conditionals to do this work inside. So it's kind of a neat thing. So this is an example. Drop last, has 2 overloads. You can pass the thing, or you can pass on the thing. It does support variable arity with ampersand. And I think the argument after that is bound to the rest of the things. That maps to a sequence, which means you can theoretically pass an infinite set of things as arguments to a function, as long as you don't try to print them or do one of those things you shouldn't do.
So if you wanted to have common Lisp optional arguments, you could just basically have something expand into one.
Really, you can build optional arguments or keyword params on this, so they are not primitive in my opinion, and they don't belong in Lambda or fun. Make macros. I'm going to talk later about references in the context of the concurrency primitives, and these are the mutable things in the language, but they're actually here because of the mapping to vars from Common Lisp. So you can have vars, unlike Common Lisp, where there's this sort of symbiosis between a symbol and the value cell and the var. That's separated in Clojure. There are vars. Vars are in namespaces. Those are the things that really have the data associated with them. Symbols are lighter weight names. Vars are named by symbols. And they have dynamic scope. They obey a stack discipline. It's exactly like Common Lisp vars, except that you can define a var at the root with def. It could be unbound. Set is restricted to apply only to vars that have been bound thread locally. Okay, so you can't whack the roots with set. Otherwise, they have the semantics of special vars.
Yeah, I don't understand. What do you mean by shared root? Fine. Verify that.
When you have a dynamic var, def var in Common Lisp, there's a root value. You could set it in Common Lisp. You could set f it, right?
Okay.
Can in Clojure. You could bind it locally, right? And the special operator for that is called binding. It's not let. So there's a special way to bind these things. When it's bound, then you can set it, and not otherwise. They can be unbound. There's really nothing special to them. Otherwise, they're extremely similar to vars, def vars, except they have real thread local semantics. It's guaranteed a binding in a thread will be distinct and invisible to any other thread. And you can use that in concurrency programming. That's a hard promise.
When you do binding for function,
Right. You get a whole new set.
Okay,
No
so
binding propagation to threads.
You get a binding.
No. Because, well, there have been long arguments about this. I decided no.
Did you effectively copy that?
No, you get a new binding set. If you want to propagate bindings to a fun you're launching in another thread, do it. Because I'm not going to do it for you.
It takes the global.
It's a new thread. It's got root bindings. Set up bindings that you want. Okay? So it's very neat. The one neat thing, though, is because Clojure is a Lisp 1, and all Clojure functions are defined with def, they're all stored in dynamic vars, which means you can dynamically bind functions in nested context. That's really cool. If you've been into context style or aspect-oriented programming, you can do that with Clojure out of the box because of this behavior. Because functions are stored in vars, you can rebind them in context. You want to, in a particular context, add logging to a function, you can do that. Change its behavior, swap out the algorithm because you know the data set's going to be unusual in this call context. Totally doable. It's very powerful stuff. And it was sort of fell out of it. It's easy.
How does Jack Clojure code that when that happens? Does it get confused or?
The thing about the JIT optimizations is, if you're calling something 3 times, you do not care, right? If you're calling it enough times in a particular context, the JIT is going to kick in and make a custom version.
Has it in practice, has it been able to do that?
I doubt it. For dynamic rebindings, I doubt it. Would I put it past them? No. No. What was neat about the JVM Languages Summit was these for some of these engineers, because they had a lot of the Sun guys and guys that work for JRocket and Azul. This is the first time they're sort of hearing the needs of these dynamic languages, the kind of stuff that would matter to languages like this. So they all were highly informed by the presentations as to, we don't do that simple escape analysis, and if we did, all these box numbers could disappear and various other things could happen. So.
We actually have time to talk about how that local bindings and
Thread locals. It's thread locals with a fast path that tests an atomic integer, right, which is spun up when things are bound. So if nobody's rebound it, there's a fast test that doesn't involve thread locals to say can't be thread locally bound fast. It's more complicated than that, but that's the short answer.
So if I have a let form and I
Yes.
define the first, I won't shadow the first function because you have to use binding.
No, it will shadow. It's still lexical, right? It's still a lexical system. In other words, I have to get all the way down and say, this thing really means that var at the root. If you've lexically shadowed it, then that shadowing happens. Otherwise, it's a dynamic system, right? It's not really lexical then. Because I don't want to muck up let. Let is so confusing when let does dynamic binding and regular binding, in my opinion. So I want people to know when they're doing this. I didn't even talk about it. There's only one let. It's let star. It's sequential let. Yes.
Talking about the dynamic variables, if the JVM ever does get through tail call, how do you use that?
It's not going to interact through. It's not going to interact through dynamic bindings.
Well, dynamic bindings plus the writing plus the
It's still in a tail position, right? It's just got to test to see if which one to call. It's still tail, right? So that still can be optimized through. There's nothing about it that's inherently non-tail. If you make a decision, then use this, and that's the tail call. It's still the tail call. It's not like you're taking the result back and then doing something with it and break. Now it's not a tail call anymore. That's the only place where you run into trouble. So I consider it optimizable, but it probably isn't yet. Okay, so I say Clojure is a Lisp 1, and it has common Lisp style def macro. Typically you would say, that isn't going to work, right? That's why Scheme has this, this hygienic system, because you're going to have these clashes. But it ends up, you have a lot of these clashes because of the way the reader and packages work in common Lisp, not because of any inherent problem. So if we separate out vars from symbols, then symbols can be really simple. In fact, they can be read by the reader and not impact the system. In other words, there's no interning happening during reading. In fact, there is interning only of the names, so that symbols are still fast comparable. But it's not interning of values or mucking with your var space. There's no value cell or anything like that. They have constant time equality. So they're fast, they're usable as fast keys and things you typically use symbols for when you're doing symbolic programming. But the reader has no side effects. It returns this. Symbols can have a namespace part, and even a namespace qualified symbol is still just a name. It doesn't say there is storage associated with this. It does not say or imply there is a var there or anything else. It's just a name with a namespace. So namespaces really are a way to just qualify names. They're not about packages or anything else. You just say my namespace / the thing, and you get a namespace qualified symbol. It's just a name. Then the trick in Clojure is there's a process called resolution, which resolves names. So now you're in a namespace. You've read in a bunch of these unadorned or possibly namespace qualified symbols. Now you need to say, what does foo mean? Okay? Now we're going to go look up the var namespace and say, okay, in this namespace, foo means this var. Okay? But we didn't mess with those namespaces just by reading some source code or anything else. It also means that macros are manipulating this name world, not this var world. So they can easily manipulate names and emit stuff into a space in which they'll be qualified where the macro is defined, and the qualified version will be what the macro emits. I'll show you that. So I call that a syntax quote. So we have regular quote. Quote foo is foo. It's just a symbol. So we're imagining a fresh REPL. Nothing's defined. Right? Back quote foo says, well, we're in the namespace user. That name, it resolves to user foo. There is no user foo yet. It's just saying this is the way the name is qualified, which means when you use back quote in macros, it's going to look up those names in your namespace and emit, again, names that resolve to what the name means in your namespace, but still just plain names. So we can see if these two things are equal, and they're not. Okay? If they don't look equal, they ain't. Right? We're not in that namespace world. We tried to use it, we can't. We didn't make any vars called foo. All right, so let's define something called foo. No problem, it gives us this. This means something different in Clojure. And now we can evaluate foo, we get 5. We can say, we can refer to foo qualified or unqualified. We're talking about the same var, so it's the same value.
Wasn't the first foo evaluated to 5?
This is 5 and 5. 5 and 5 are equal, still,
user foo evaluates.
even in Clojure. Yeah, user foo is just a fully qualified name. We're in the user namespace. So this will resolve to user foo because we did this. And we did this when we didn't get an error. In fact, if there was already a foo in this namespace, this would have failed. Clojure is stricter about names existing before you use them. So this works. We can resolve foo, right? In this namespace, what is foo name? This is a var, right? I said sharp code is different. This is the var, the actual var that's in the namespace, that has the value in it. So we name them like this, and the var is called user foo. A var always has a namespace qualified name.
So vars are objects.
Everything is an object, but vars are the places where the stuff gets stored.
And
Not
what
symbols.
is the current namespace name? Is that
You're in a
global standard?
namespace, and we're presuming we just started the REPL, so we're in the user
How
namespace.
do you know what namespace you're in or change what namespace you're in?
There's all kinds of functions for that. In namespace, find namespace, you can change namespaces. It's a lot like Common Lisp that way,
The
where you can
global
move around.
state, you can set to it,
It's thread local state, because it's bound. So it's thread local, and it will unwind when you do a compilation unit. So in a compilation unit, you can say, I'm in this namespace. The current namespace gets pushed, gets bound, a new binding gets pushed and popped. So it's not global. There's no trashing from other threads.
So you have to define a namespace before you remove this symbol as qualified.
No. You can say anything you want. These are plain names. Until you get to resolution, it's fine, which is really the way it should be. Right? Who cares? It's this name. In fact, you may want to use it because it names something in some XML file. They're names. Symbols as names are more useful than symbols that are bound to be vars. The only cost really is the reader can't read pointers. Right? The Common Lisp reader can effectively read pointers. That's a cool thing. It has a huge cost.
Yeah, what do you mean pointers?
If I read, right, I read a symbol. It gets interned. It's storage. If I read that in another file, I get the same storage. Okay, just by reading, I have 2 pointers to the same storage. Right, which is cool, and there's some Common Lisp code that leverages that. You can't do that in Clojure.
Okay.
It is a cost. Yes.
The videographer page you paused for about 30 seconds. So I
Okay.
changed